Today we are going to discuss about boundary layer theory. My name is Dr. G.V. Rao, Professor in the Department of Civil Engineering, Vijnan Institute of Information Technology, Duvada, Visakhapatnam. Today we are going to discuss about boundary layer theory. Right, these are the important points related to the boundary layer theory. First we are going to discuss about relation between shear stress and velocity gradient. What is ideal fluid? What is real fluid? Definition of boundary layer, parts of boundary layer, and development of boundary layer along the length of the flow, along the direction of the flow. That is, what is laminar boundary layer? What is turbulent boundary layer? What is laminar sublayer? And also we are going to discuss about what is laminar zone, what is turbulent zone, and what is transition zone. Relation between shear stress and velocity gradient. Right, this is the formula. Shear stress tau is equal to mu into du by dy, where tau is the shear stress, mu is the viscosity of the fluid, that Newton second per meter square, and du by dy is the velocity gradient. Now, if this is the solid boundary, the velocity over the boundary is equal to u is equal to 0 if y is equal to 0. At a distance y is equal to 0, velocity is equal to 0. Away from the boundary and normal to the boundary, velocity develops. Once velocity develops, this is the velocity here, and velocity increases here. Velocity increases gradually, velocity increases away from the boundary. Suppose this is the velocity u over this layer. This layer, the velocity is u, this is du. The velocity over this layer is u plus du. The velocity over this layer is small u. The velocity over this layer is u plus du. Therefore, velocity gradient develops, that is equal to velocity gradient is equal to du by dy. Right, therefore, shear stress is equal to tau into mu into du by dy. At y is equal to 0, u is equal to 0, automatically shear stress is equal to 0. This is the relation between the shear stress and the velocity gradient. What is ideal fluid? What is real fluid? Ideal fluid is the fluid. It is assumed that there is no viscosity. There is no viscosity means, suppose the fluid is moving over the solid boundary, there is no contact between the solid boundary and the fluid, because ideal fluids are not having viscosity. If there is no viscosity, there is no bond between the boundary and the fluid. Therefore, the fluids, ideal fluids flowing over the solid boundary, that are slip smoothly over the solid boundary. There is no contact between the boundary and the fluid. Ideal fluid. Right, now, when a real fluid means fluid is having viscosity. When a real fluid flowing over the solid boundary, there is a contact between the solid boundary and the fluid, because real fluid having viscosity. Because of the viscosity, the real fluids flow over the solid boundary that are stick to the solid boundary. Therefore, the velocity over the solid boundary is 0. Velocity is equal to 0 at y is equal to 0, because there is a contact between the boundary and the fluid. Fluid is having viscosity. Right, in case of ideal fluids, there is no contact between the fluid and boundary, whereas in case of real fluids are viscous fluids that are having viscosity. Therefore, that real fluids are stick to the solid boundary, and at y is equal to 0 or over the boundary, the velocity over the boundary, velocity is equal to 0. Once the velocity is equal to 0, tau is equal to mu into du by dy. velocity v is equal to 0 over the boundary, that is equal to y is equal to 0, automatically there is no velocity, automatically shear stress is also 0. In case of real fluids, over the boundary, shear stress is equal to 0 because velocity is equal to 0 because of the viscous effects between the boundary and the fluid, automatically du by dy 0, therefore shear stress is equal to 0. This is the difference between the ideal fluids and real fluids. If the boundary is stationary, the velocity of the fluid at the boundary will be 0. Suppose this is the boundary, the velocity of the fluid, that means y is equal to 0, velocity is equal to 0 over the boundary. Right? Normal to the boundary, away from the boundary, the velocity gradually develops. Okay. If the boundary is stationary, the velocity of the fluid at boundary will be 0. Further away from the boundary, the velocity will be higher, and the result of this variation of velocity, therefore here velocity is equal to 0, here velocity is equal to 0, velocity increases, so some one point that velocity reaches to the free stream velocity. Right, first point. If the boundary is stationary, the velocity of fluid over the boundary is 0 because there is a viscosity. There is a viscosity between the boundary and the fluid. Away from the boundary, the velocity gradually develops and velocity increases. Because of this over the boundary, the velocity is 0, away from the boundary or normal to the boundary, the velocity gradually develops. The result of velocity variations from 0 to increased velocity, there is a formation, there is a development of velocity gradient. Once velocity gradient develops, shear stress is equal to what? Shear stress tau is equal to mu into du by dy. Once velocity changes from 0 to u, automatically du by dy exists. The result of velocity variations develop the velocity gradient du by dy, automatically shear stress exists. Shear stress is equal to mu into du by dy. Once we have the du by dy, automatically shear stress is also, we are going to get it. Right. Next one. Now, the variations of velocity 0 to free stream velocity. Suppose this is the boundary, the velocity over the boundary is 0, at y is equal to 0, u is equal to 0. Normal to the boundary, away from the boundary, gradually the velocity increases. At one location, the velocity reaches to the free stream velocity. This is free stream velocity u, that is flow over the solid boundary. Over the solid boundary at y is equal to 0, velocity is equal to 0. Gradually velocity increases away from the solid boundary on normal to the solid boundary. At one point that velocity reaches to the free stream velocity. Right? Boundary layer means the variation of velocity from 0 to free stream velocity normal to the boundary takes place at a narrow region, that is vicinity of the boundary, takes place at a narrow region and also vicinity of the boundary. This narrow region is known as a boundary layer. This narrow region is known as a boundary layer. The theory related to this narrow region, the theory related to this boundary layer is known as boundary layer theory. Right? Next point, parts of boundary layer. So what is boundary layer? Boundary layer means the variation of velocity from 0 to free stream velocity in the direction normal to the plate takes place in a narrow region. In the vicinity of the solid boundary, this narrow region is known as boundary layer. Okay, the theory related to this boundary layer is known as boundary layer theory. Right now this is the boundary. The velocity normal to the boundary gradually increases. At one point reaches to the free stream velocity. At one point, this is reaches to the free stream velocity u. This is the boundary layer. This is the boundary layer. Beyond the boundary layer, the velocity, there is no change. That free stream velocity is maintained here. So that what is happening up to the boundary layer, this is part 1. Above the boundary layer, this is part 2. Up to the boundary layer, the shear stress is equal to tau is equal to mu into du by dy. This is the standard formula. The velocity gradually varies from 0 to free stream velocity because we have du by dy within the boundary layer. Once we have the du by dy, automatically shear stress also develops. Okay. Beyond the boundary layer, there is no change in velocity. There is no change in velocity. Automatically, du by dy is equal to 0. Therefore, shear stress is equal to mu into du by dy. Du by dy is equal to 0. Automatically, shear stress is equal to 0. There is no shear stress. There is no shear stress above the boundary layer. Below the boundary layer exists the shear stress. Right? Development of boundary layer in the direction of flow. Now we are going to discuss about development of boundary layer in the direction of flow. Right here, the development of boundary layer in the direction of flow is divided into different parts, different layers, that are, first one is the laminar boundary layer, turbulent boundary layer, and laminar sublayer. 3 zones, right? From this point to this point, this is the laminar boundary layer. From this point to this one, this is the turbulent boundary layer. And also in between we have, this is one layer, this is known as transition zone, and this is also known as transition boundary layer. This is very small, therefore this is neglected in our calculations. One is laminar boundary layer, another one is the turbulent boundary layer, and one more layer, that is the laminar sublayer, that is the part of turbulent boundary layer. This is the laminar sublayer. Laminar boundary layer, turbulent boundary layer, laminar sublayer. And this is also divided into 3 components. One is laminar zone. This is the laminar zone, transition zone. This is the transition zone. This is a turbulent zone. Laminar zone, transition zone, turbulent zone. These are the divisions of the boundary layer along the length of the flow. Right? Now here we are going to discuss, the first point is, consider a flow of fluid having a free stream velocity u, having a free stream velocity u, and provided a thin smooth plate parallel to the direction of flow, smooth thin plate parallel to the direction of flow. If we are provided one smooth thin plate parallel to the direction of flow here, now what is happening? The free stream velocity flow over the surface of the boundary, because the boundary is stationary, the velocity of flow over the boundary is also 0. That means over the boundary, the velocity u is equal to 0, because stationary, boundary is stationary, the velocity of fluid over the boundary is 0. But away from the boundary, normal to the boundary, the velocity gradually increases. Right, this is the boundary, the velocity gradually increases. Once the velocity increases, what is happening? Velocity gradient develops. Du by dy exists. Once velocity gradient exists, shear stress also develops. Tau is equal to mu into du by dy. We have du by dy. Automatically shear stress is also developed. Okay. Then the velocity of the fluid on the surface of the plate should be equal to the velocity of the plate, but the plate is stationary. The velocity of the fluid on the surface of the plate is 0. Okay, clear. And next point, but at a distance away from the plate, fluid is having certain velocity, thus the velocity gradient develops over the surface of the plate, right? Definition of laminar boundary layer, right? The free stream velocity flow over the solid boundary, over the surface of the boundary, the velocity is 0 because the plate is stationary. Shear stress exists. That shear stress retards the flow. Shear stress retards the flow. Therefore, this is the leading edge. This is the leading edge of the solid boundary, right? Near the leading edge of the solid boundary, and where the boundary layer thickness is small, near the leading edge of the solid boundary, where the boundary layer thickness is small, the flow in this layer is laminar. The flow in this layer is laminar. Even though the main flow is turbulent. Even though the main flow is turbulent, therefore the boundary layer, this layer of boundary is said to be laminar boundary layer, right? Next one, definition of laminar zone. What is the definition of laminar zone? The length of the plate from the leading edge up to which the laminar boundary exists is known as laminar zone, right? This is the length of the plate. This is the length of the plate. This is known as laminar zone. Okay, right. The laminar zone is estimated by using the Reynolds number. What is the formula for the Reynolds number? Re is equal to rho V d by mu. Rho is the density of flowing fluid. Suppose water, rho equal to 1000 kg per meter cube. V is the velocity of flow. D is the diameter in case of pipe flow. Whereas here D is nothing but the distance between the leading edge up to the boundary layer, laminar boundary layer exists. That means this is known as x. Here D is nothing but x, and mu is the viscosity of fluid. Viscosity of fluid, that is varies from liquid to liquid, fluid to fluid. Right now, laminar zone is estimated based on the Reynolds number. That means if the Reynolds number Re is taken as 5 into 10 power 5. Suppose Re is taken as 5 into 10 power 5, that in Re is equal to 5 into 10 power 5 is equal to mass density value into velocity of the fluid into D divided by mu. All values are given, but the Reynolds number value is taken as 5 into 10 power 5 is equal to rho velocity of the fluid into viscosity. We are going to determine D. Here in place of D, x. This distance is nothing but laminar zone. Okay, are you clear? If the Reynolds number is more than 5 into 10 power 5, corresponding distance x is known as turbulent boundary layer. Definition of transition zone. Definition of transition zone. Right here, beyond the laminar boundary layer or beyond the laminar zone, the boundary layer is unstable. The boundary layer is unstable. The flow in this area is disturbed and irregular. Therefore, the laminar zone is transferred to turbulent zone in this small area. In this small area. Are you clear? The laminar boundary layer is transferred to turbulent boundary layer within this small zone. That zone is known as transition zone. Turbulent boundary layer. What is the definition of turbulent boundary layer? Beyond the transition zone, the boundary layer gradually increases. The boundary layer thickness gradually, continuously increases, and the flow in this area is turbulent. The flow in this area is turbulent. This zone is known as turbulent boundary layer. Okay, and the distance beyond the transition zone, that is turbulent zone. Right. Laminar sublayer. This is the region in the turbulent boundary layer and adjacent to the solid boundary and the velocity variations in this laminar sublayer, is because of viscous effects. Okay. The velocity variations in this laminar sublayer is because of viscous effects, but the velocity distribution in this laminar sublayer is parabolic, and the thickness of the laminar sublayer is very thin, very less. The thickness of the laminar sublayer is very less. It is assumed that the velocity variations in the laminar sublayer is linear. And du by dy, that means velocity gradient is constant. Right? In case of laminar sublayer, exists boundary layer shear stress. What is the boundary layer shear stress? Now I am explaining here. Shear stress tau is equal to mu into du by dy. Right, now this boundary layer shear stress means the velocity variations in the laminar sublayer is linear, then the du by dy is constant, du by dy is constant, therefore du by dy is equal to u by y. Therefore, boundary layer shear stress tau 0 is equal to mu into u by y. If strictly speaking, at y is equal to 0, over the boundary, shear stress is equal to 0, du by dy is equal to 0 in general case. But here, over the boundary, that also the velocity variations are affected by viscous forces. Even though shear stress having here, that shear stress is known as the boundary layer shear stress, that is equal to tau 0 is equal to mu into u by y. Right? Thank you. Thank you one and all. This is about the boundary layer definition, boundary layer theory, different parts of the boundary layer.